Hello everybody, welcome to our video solution to problem 3 from quiz 12 here in spring 2023, Math 302 at Cal State Fullerton. So let's see, we have an integral domain R. So remember that an integral domain, okay, so we're talking here, we have an integral domain. This means that R is a commutative ring with identity. And it has this zero factor property, right? So, and if A and B are in R, such that A, B is equal to 0, then A equals 0 or B equals 0. Okay, so we're not talking about like matrix rings, right? Or Z mod 6Z. So let's see, part A, every field has the property that if a product of two elements equals 0, then one of the factors equals 0. All right, that's referring to this line here. Okay? So every field has this property as well. The question, is R necessarily a field? So we know R is an integral domain. We want to know if it's a field. Fields have the same property here, right? And this is just simply a matter of trying to work out which class of rings is in which, right? So is every field an integral domain, or is every integral domain a field? So we know that a field is a commutative ring with identity. We also know from what it says here that it satisfies the zero factor property. So in fact, if you are a field, then that implies you are an integral domain, right? Every field is an integral domain. But is the opposite true? Just because you're an integral domain doesn't make you a field. And the answer is no. So no, and why? Well, we need to give a counterexample. So the set of integers is an integral domain, but it's not a field. Why is it not a field? Well, to be a field, every non-zero element has to have an inverse in the ring you're talking about, right? So 2 is an element of Z, and 2 has no inverse in Z, right? And we're talking multiplicative inverse. Okay, so there we go. So the answer is no. Is R necessarily commutative? Well, yeah, that's actually part of our definition. One could try to write down a definition of an integral domain, but dropping the assumption of commutativity. Of course, that's a thing. However, that's not our definition of integral domain, right? Okay, C. Let x, y, and z be in the ring. Okay, so we have 3 elements. X is not 0. And x times y is equal to x times z. We want to prove that y is equal to z. So this is what people would talk about canceling, right? Oh, they say, oh, cross these out. Which, by the way, I really, really hope that you don't cross stuff out, okay? I think we should be trying to teach our students not to cross off things so that they can't see their work, all right? Anyhow, whether we cross it off physically or not, this is given a name. This is called the cancellation law. Now, one of the ways that people are going to typically think of how to go from xy equals xz to y equals z is by dividing by x. And we're in a ring. We don't really know if we have units here. Yeah. So other than the identity, so canceling shouldn't be about dividing. In fact, we are going to use this zero factor property. So the way we do this is by saying, well, okay, if xy is equal to xz, then instead of dividing by x, I'm going to subtract xz. Okay, but now I can use the distributive property to factor out an x. And now instead of dividing by x, I simply use the zero factor property. Say, well, since I have an integral domain and I have a product of elements, x, and the difference of y and z, and their product is equal to 0, I know one of the factors is equal to 0. So since R is an integral domain, x equals 0 or y minus z is equal to 0. Okay, but this contradicts the assumption that x is not equal to 0. Okay, so it's not that one. So we get this, y minus z equals 0, but that implies that y is equal to z. And there we go. We have our cancellation law. All right, we'll see you next time.